Okay, so it's our pleasure today to have Joan Bruna give today's 1W-MINDS seminar. So he's a professor of computer science, data science, and math at New York University. Uh, he's very well known for his influential research on machine learning and signal processing. He's won numerous awards for his research, including the Sloan Fellow and the NSF Career Award. So today he'll be talking to us about on the learning complexity of Gaussian multi-index models.
Okay, thank you, Wele, and the rest of the organizers for inviting me. So yeah, today I'll be talking about this problem, this question of how can we learn efficiently in certain class of functions in high dimensions. And before I start, let me just say that this is a joint work between a series of collaborators. So Alberto Bietti, who is at Flatiron Institute, Alex Damian, who is a PhD student at Princeton University, Loucas Pillaud-Vivien, who is a professor in France, and then Jason Lee, a colleague from Princeton as well. All right. So the starting point and the backdrop of my talk is really to the placing the context in this world era of neural networks today, where neural networks are used in a very, let's say, in a very peculiar and interesting way from a mathematical perspective, in the sense that neural networks are used in the following way, right? So we typically consider a very large data set of, in that case, for example, here, text, and we train the neural network to solve a task that a priori has nothing to do with what we want to use it later, right? So in particular, here we train the neural network to predict the last word, right? So this is a task that a priori is unrelated to what we, maybe want to do it for other things, let's say dialogue, etc. So the whole premise here, right, is that we are using this neural network for this particular task to extract a useful representation, right? And we hope that this useful representation can be transferred to something else, right? And this happens in the language, but also happens in many applications right now in vision. And this is perhaps the defining characteristic that sets neural networks apart from other traditional ways to learn to extract information from data. For example, kernel methods, right, in which the representation is something that is built and in a sense crafted by the learner, right? And so there's no ability to this notion of pre-training and downstream adaptation doesn't even make sense. So the overarching question of this talk today is how can we understand this phenomena, right, in the context of modern neural networks that are trained using gradient descent. And obviously we are going to focus on very simple class of neural networks for that. In particular, the simplest ones that we can try to study that have this property. And then we are also in the second part of the talk, we are going to maybe take a step back and try to place this ability of neural networks to solve this feature learning problem and try to compare it against some notion of optimality, right? And we are going to try to, in a sense, relate it to questions that are more in this modern perspective in statistics that try to combine to characterize what we call these computational to statistical gaps. All right, and let me also say that if anyone has a question anywhere during the talk, please feel free to interrupt. I mean, it would be great to have it kind of informal style. So please do not hesitate. So, okay, so this question about try to understand what neural networks can do or cannot do is very far from being a new question. It's actually a field. It's a class of it's a class that has been studied by mathematicians, statisticians alike for many years. And so, in particular, the neural networks that are the ones that the initial focus for us are going to be these shallow neural networks, right? That only have one hidden layer. So one can view these, one can describe these functions as those that can be written as a linear combination of rich functions or simple functions that take the input, high dimensional input, just project it into one direction and then pass it through some fixed nonlinear function. So the first thing that the community really understood very well are approximation properties of this class. Right. So, for example, everyone here, I guess, is familiar with this universal approximation property, meaning that this class can approximate any function, with the slightest amount of regularity, like continuous functions can be approximated as the number of terms goes to infinity. And we also understand the rate of approximation, right? So for traditional classes of functions, spaces like, say, functions that have a certain number of derivatives, we know that this rate of approximation, in fact, is very bad. And the also thing that, like, one of the, let's say, first very important results in this area was, was done by Andrew Barron more than 30 years ago now, that we really understood. It's the first, in a sense, the first instance of feature learning, right, in this modern language, which basically showed that in this class of neural networks, one, as I said, this class has parameters, both in the way where we define these neurons, like the directions in which we project the data, and also obviously the coefficients that we use, to build this linear combination. So the traditional approximation theory is concerned with just trying to optimize these coefficients, these linear coefficients, with the positions of the neurons fixed. Whereas if one considers this like nonlinear approximation, which tries to adapt the set of neurons to the target function, one can obviously get a better approximation. So Andrew Barron was able to quantify this gap, right, and show that in fact there's a very interesting class of functions, right, that are functions that intuitively are the functions that I can approximate, that I can build with a small number of neurons, right? And small number here of neurons means that I can, in a sense, have an integrable number, like I can put the density over the parameters and have something that is integrable. So in that, we have this, we had this, in a sense, very first important result that was neural networks are, one can perform feature learning, can really boost the approximation power for certain classes of input space, all right? We also saw that a few years later, we could see that this class of functions, right, that now we can view it as from this integral representation, was also some space for which one could do statistical learning theory, in the sense that what could also control the estimation errors, right? Meaning that not only I can approximate efficiently in that class, I can also estimate functions efficiently, estimate functions with good statistical efficiency in that class. The last thing of the puzzle, right, was computational, right, algorithms. And a few years later, like just a year later, there was a series of very nice papers that tried to actually provide a description, like formalize the description of how is it possible to perform feature learning in this class, right? And they use this beautiful framework that tried to cast the optimization of the neural network in the space of densities, right? By just viewing, instead of viewing the network as a collection of parameters in the neurons, they just express the neural network through the empirical measure determined by the position of the neurons. Okay, so this was very nice, but however, this is there's a kind of a roadblock here, right? In the sense that this framework that tries to understand how we can perform feature learning with this gradient flow, in fact, is fundamentally qualitative, in the sense that there's actually an inherent harness to find the best nonlinear approximation. Okay, so in other words, one can actually find functions that are easy to approximate with a neural network, yet we can show that it's computationally hard to find this best approximation. Okay, so somehow this means that if we want to understand, like, get like positive results that concern the whole learning, including obviously the algorithm, maybe we need to go a little bit beyond this class of approximation. Okay, and this is where now we start entering the subject of these single index models, right? And this is the first class of functions that we are going to familiarize ourselves. Okay, so here now we are going to make the setup a little bit more concrete, right? So we are going to assume that the input distribution is Gaussian, right? It's kind of a canonical example of a high-dimensional distribution, data distribution. And we assume that the labels, the observations, are generated by a target function f star and some noise. And this function f star, in fact, is just a composition of one-dimensional projection with an unknown nonlinear function. Okay, so in some sense, we have in the target function, there are two things that are very different. There's a high-dimensional parameter, which is this direction, this hidden direction. And then there's also some unknown non-parametric object, which is this like scalar function. Okay, and so this is in some sense like perhaps the simplest instance, right, where one could try to understand this mystery of feature learning. Okay, here clearly this target function secretly depends on a very interesting feature, which will be just projecting the data into this direction, theta star. Okay, and so one can try to understand the question of when can I efficiently solve this semi-parametric problem, right? And this semi-parametric problem, by this I mean that one needs to, at the same time, find this hidden direction and also find this nonlinear function that is scalar. Okay, and so how can we actually try to solve this problem efficiently using this notion of gradient descent methods? All right. So for this, there was a very beautiful series of work that was mostly pioneered by Daniel Tsu and Dudeja, and then also my colleague Gerard Benarous and Reza and Okosh Ganamath. And so let me try to describe it to you, because it's in a sense something quite important that we are going to build on in the rest of the talk. Okay, and here first let's try to understand this something kind of a simplified version of this question, right? So let's first assume that we have infinite amount of data, right? So we have to essentially just try to find this hidden direction in the regime where we have in the infinite data regime. And let's also assume that we know this nonlinear function, right? So the problem is really reduced to just estimating this hidden direction theta. So here we have now a very simple, and we try to solve this problem using least square, just the mean squared error, right? So we have a function over the sphere that is defined by just finding the correlation between our, let's say, hidden direction and the target direction. Okay, and so we decompose this square. And we find that basically the most important, like the key thing here is to understand this correlation, right? So how can we find the correlation between these two single index functions, single index models? And so this integral in fact is of course over all the variables, right? But because here we are only inside, there's only the projection with respect to theta and theta star, it's obvious, right, that this integral becomes just an integral in 2 dimensions, right? That is the space spanned by theta and theta star. And so if one just does a little bit of rewriting this 2-dimensional integral, one can write it in terms of a very well-known object, which is this Orsten-Uhlenbeck semigroup. Okay, so it's one can view that this correlation, in fact, is just some quadratic form with respect to this semigroup, right? And so this equation essentially says that what matters really here is just the overlap, the correlation, the angle between theta and theta star, and then the object that appears is some kind of a Gaussian integral or Gaussian convolution, right? It's just some, this expectation here just amounts to convolving the function f and then applying an appropriate dilation, okay? So in fact, we know many things about this semigroup. In particular, we can find its we can totally determine its eigenfunctions, right? So this semigroup, in fact, has a joint diagonalization, right? So the basis that matters here is the basis of Hermite polynomials, right? Which are eigenfunctions of this semigroup. And so once we have this structure, in some sense, we have already solved the problem. Because if now we take our link function, we can expand it, decompose it into this system of eigenfunctions, right? And then plug this decomposition back into our loss. And we see that everything now just becomes completely explicit, right? And so now here our loss is expressed explicitly in terms of this overlap, this angle on one hand, and on the other hand, obviously the coefficients, this alpha j, they are completely determined by the regularity of the link function, right? So basically the part of the problem that involves the direction is captured in this angle, and the part of the problem that depends on the link function is just captured in this expansion. And so now we can, in some sense, completely determine the geometry of this optimization problem. And so here, the landscape of this function here now is, we can completely read it off from this equation, right? So we have, in fact, a saddle point at the hemisphere, right, which correspond to the places where m equals 0. And the order of this saddle point, in fact, is given by the first coefficient in this expansion, right? So when m is very small, what matters here is the leading term, right? It's the first non-zero term. And this is what, in this paper by Gerard, it was referred as the information exponent, right? It's the first degree that is non-zero, right? Where this expansion is non-zero. All right? And so the idea here, the picture, right, is that the picture here is that if now I'm going to try to analyze how an algorithm would work for how gradient dynamics would work here, I would start an initialization, right? So an initial point in my optimization is going to be some guess for theta that is generally going to be very close to this equator, right? In fact, it's going to be a distance 1 over square root of d from this equator. And then I'm gonna place it here, and then it's gonna essentially take a certain amount of time to escape the region of mediocrity, right? The region that is nearby the saddle point. And the time it takes to escape the saddle point obviously depends on the order of the saddle, right? And once we have this picture for this very simplified problem, in fact, just by applying relatively standard tools, we can translate this result into a guarantee in terms of sample complexity, right? So the consequence of that is that if I have a number of samples that is of the order of this d to the L, right, with L is this information exponent, then even if I have, so the empirical landscape, which you can view it as a noisy version of this, is still going to be, the algorithm is still going to be able to escape the mediocrity. Okay, so that's the picture. So this is something that is in a sense was known in these papers for the single direction, right? So now the question is, how can we go from this picture to the picture where we have maybe perhaps more than one hidden direction, right? So this is what brings us to the multi-index models. Okay, so the multi-index model in some sense is just the natural extension of single index models, where instead of having here a hidden direction, now I have a hidden subspace, okay, of a dimension. You can think about this dimension to be still very small. And instead of having here a scalar function, now I have a function of a q variables, right? So it's still a low dimensional function, but it's no longer scalar. But in some sense, it still looks like a very reasonable, like a very similar model from before. And so here now we are also going to be focused on two natural problems, right? Two natural estimation problems. One in which I can maybe give to the learner, already I'm going to tell you what is the true nonlinear function, right? So here it's more like a problem where one just needs to recover the missing subspace, like the hidden subspace. And then there's also a very natural problem that is maybe a bit similar to what kind of a neural network would do, right? Where I don't assume that I know anything about the target, and I'm just trying to learn both things at the same time. Okay, both the subspace, which would correspond to kind of to the first layer of my network, and then the low dimensional function that I put on top, that I'm gonna call my second layer, right? So you will notice here that it's a relatively abstract notion of neural network, right? But I can still formally view it as a two-layer neural network, right? Where this is a subspace and this is a low-dimensional function. All right, and just for those who are wondering, because I'm learning these two things at the same time, you will notice that I can there's an undetermination here, right? That I can just change the basis of my subspace, right? Because I have a kind of an undetermination on this composition, which means that I can reduce myself to learning in what's called the Grassmann, which is just the quotient of the Stiefel, like Stiefel manifold, with respect to changes of basis, right? But this is not important. All right, so what changed, right, from one model to the other? All right, so let's see what's changed. So we can revisit the Orsten-Uhlenbeck semigroup, right? So remember that we defined the semigroup to be this Gaussian convolution, right? And so if you remember, the thing that we saw is that if you give me a pair of scalar functions, and we define this operator that just essentially takes a scalar function and defines a single index function, then we can relate the correlation of these single index functions in d dimensions to a correlation in the intrinsic dimension, right, which is in 1D. And for this, to make this translation, we need to use this semigroup. Okay. All right. Now there's a natural extension, right, where instead of having things that are scalar, I can just have things in dimension q, right? So I have two functions that are in dimension q. I have two subspaces that are of dimension q that live in RD, and then I can exactly do the same, write the same equation. So I can try to relate the correlation of these multi-index models in terms of their intrinsic dimension, right? Which is Q. So indeed, I can just rewrite this in a product, and indeed I can do it by using the natural extension of this semigroup, right? So now I have again I need to modify this function with an operator that instead of being just parameterized by a single angle, now it's going to be parameterized by the matrix of all the angles between the subspace, right? So if I now take two subspaces of dimension Q and I look at their inner product, I have a matrix of Q by Q, which captures kind of the angles between the subspaces, okay? And the definition of this new semigroup, right, is just exactly what you would expect, right? So I just have a Gaussian convolution, right? But of course here the covariance depends on this angle. So this looks at this point pretty similar, right? So it seems that the kind of the main machinery that we use to understand the single index model might be actually sufficient to understand the multi-index setting. But there's a key difficulty here. There's a key difference, right? That you might have guessed is that now we have lost the commutative structure, right? The semigroup is a metric semigroup, right? So I no longer have the commutative property, right? And so what it means is that I have lost this ability to just find a single system of eigenfunctions and just write all the laws explicitly in terms of this system, okay? So what I need to do some extra work. So one thing that we can do is that we can try to make it quite explicit. What is the part of this correlation that stays commutative, and what is the part that now I need to worry about in terms of non-commutativity. So if we take this Gram matrix of the subspaces, in fact we can gain a lot of insight, a lot of information by looking at its SVD. Right, so if we look at the singular value decomposition of this Q by Q matrix, in fact, here we identify what's called these, the singular values of this matrix correspond to what we call the principal angles between the subspaces, and then U and V correspond to respectively the bases in each of the two subspaces that I need to make the alignment. All right. So now we can take this correlation remember that this is really what appears in the laws. And I can view this correlation. I can express this correlation by making appear explicitly this coefficient on the SVD. Okay, so we see that now we have we have extracted from the SVD. We have extracted kind of a commutative core, right, which is the diagonal of the M, right. So if we use the SVD, we can in a sense still recover something that is commutative. And so this semigroup, like if we just restrict ourselves to diagonal matrices, then we still have a joint diagonalization property using a tensorized basis of Hermite polynomials, right? So we can just take our Hermite polynomials that we had before, and then upgrade them if you want to polynomials in Q variables, and this defines a basis that diagonalizes this semigroup from the diagonal setting. So just to summarize, right? So here what we have is that we have to deal with some, in this inner product, we have to deal with two completely different sources of the correlation depends on two completely different things. One is how much the two subspaces, taken in the Grassmann, how far they are, right, in the Grassmann manifold. So this is some kind of like an inter-subspace misalignment. But then it's also important to understand how the internal bases of each subspace are going to be related with each other, right? If we want to correlate functions. All right. So just as a recap so far, just to make sure that I'm not losing anyone. So here's what we have discussed so far, right? So we have some very simple L2 laws, right? That in both cases, right, depends on this operator that just takes a scalar function and brings it into high dimensional space. We have identified the semigroup that is kind of inside this loss function and used the Hermite decompositions to try to represent this semigroup, right? So in a way that now the summary statistics of the problem are explicit, right? So here you can see that the summary statistics is just a single coefficient, right? It's just the angle, and here the summary statistics are obviously this Q by Q matrix. So what is the impact on gradient dynamics, right? So what we want to understand is how much of the problem now is harder in the multi-index setting. So let me first start by looking at something that presumably seems the easier problem, right? It's a problem where I have already find the perfect second layer coefficients, if you want, and I just need to move the first layer coefficients. And in fact, remember that when Q is 1, so the single index setting, that was basically the problem that I just explained to you, right? I was fixing the length function. And there I told you that, in fact, this landscape is benign in the sense that there's only one saddle point, right, at the equator. And then outside the saddle point, in fact, the loss really has this perfect, like a dreamlike form, right? In the sense that it's a monomial, it's a sum of monomials, and all the coefficients here are positive. Okay, so there's all the coefficients are non-negative, right? Which means that if I just initialize in the top half of the equator, then I'm done, right? Because I know that I'm going to be evolving in a landscape that whose only local local minimum is going to be at the m equals 1. Okay, this is no longer true when I go to the multi-index setting. Okay, so as long as Q is bigger than 1, right? So then we can actually show that the landscape has spurious critical points, right? In the sense that for uniform initialization, right? So for random initialization, with high probability, we can trap gradient flow into a bad local minimum. Okay, so in other words, we don't recover the true subspace by just following gradient flow. And the reason for this is, at the end of the day, it's not surprising, right? Is that when we write the loss, okay, because we have now to deal with what I told you before, right? With this alignment of the bases, if we look at the loss here, we have in fact oscillations in the sign, right? So when U and V are, different bases, there's no reason why this coefficient and this coefficient should agree, right? And so in some sense, these sign oscillations is what really causes all the trouble. And here are just some examples to illustrate what's going on, right? So this, for those of you who might be familiar, in effect is the same phenomena, is reminiscent of this problem of procrasters, right? Which consists in taking some structure, right? Some function, some image, and trying to find the best alignment, right? So I have an image and I have a rotated version of the image, and I'm asking the question, can I align these structures with gradient descent? So you can see that if the image has things that look like quasi-symmetries, right? Things that look like almost like a good alignment, but in fact not a good alignment, it's very easy to get the gradient descent trapped here. Okay, so this is exactly what's happening in this setting. Okay, so this is in a sense looks bad for this kind of optimization problem. Is there any dream at this point you could try to be a little bit optimistic, right? Say, okay, if the simpler problem is hard, what's going to happen with the presumably harder problem? But in fact, joint learning in this context, in a sense, is what's going to save us, as I'm gonna show you now.
John,
Yes.
sorry for interrupting, but there's a question in the chat.
Sure. Can you? Oh, so let me see if I can find the chat. Sorry. Yes, chat. No. How does on K? M to the K? Sorry, let me see if I find again. Yeah, I guess, Anna, are you talking about this expression?
Yes, yes. I was just confused because I thought the M was just quantifying the inner product between the angles, but here it seems like dependent on the specific, yes, expansion.
So yeah. So here, okay, so good question. So the problem in some sense has a hidden variable, right? Which is just the alignment between my current choice, my current theta and theta star. And then what this expression says is that in fact the loss function, right, that you are trying to optimize depends on M through these series, right? In fact, M appears, it's not just a linear function of M, if that's what you mean, right? There's all the harmonics of my target function are going to involve different powers of M. I don't know if that makes sense, right? But then now the point is that would be trying to optimize, to minimize this function. Right?
Oh, yes. Okay, I get it. Thank you.
Okay, yes. All right. So now let's try to see how much we can save the day by moving into a different, presumably harder problem, but you will see that might give us actually some better structure. Okay, and so all right. So here we are gonna now look at the population loss, right? Again, and now we are moving these two parameters at the same time, right? So we are a priori moving both the second layer and the first layer. And now what we observe is that this function, if I just view, phi as a vector in a certain, vector, like in the vector space of like functions in dimension Q, in fact, it's quadratic with respect to phi. So which means that I can instantly optimize, I can find, so given W, right, given the current subspace, I can have a closed form optimization of the second layer weights. And then plug this second layer weight, optimal second layer weights back into my loss. Okay, so I can solve perfectly the second, like, the convex part of the problem, and then plug the solution back into the loss. Okay, so now this becomes just a function, right, that does no longer depend on phi because I kind of optimized it out, and then it's just a function of the W. So everything looks, it still looks similar than before because it still depends on this, semigroup, metric semigroup. But now there's a major difference, is that now the summary statistics have been replaced by the gram metrics of the summary statistics, right? So I have replaced M by M transpose M, which is now symmetric. And the symmetric metrics means that the bases of the subspace are aligned, right? So suddenly now I have this very powerful structural property that I recover from before, right? The fact that I can view my loss now as a sum of things that maybe depend on some, alignment, like some angle between subspaces, but now the coefficients are not negative, thanks to this alignment between the subspaces. And so as a result, we can use this extra property to show that now this landscape is well posed, right? It's a non-convex landscape, but all the local minima are global, right? So basically, in some sense, generically, one could hope that if you just throw gradient flow there, it's gonna essentially find the global solution. Okay, and in fact, we can read more information out of this problem. We can in fact view that you can characterize all the saddle points, and the saddle points are essentially subspaces, right? That have where this object here, this M, is in fact a subspace, right? So basically, these correspond to W's where a few directions have been completely aligned and some directions are completely orthogonal. Okay, so these are these saddle points. And so now, in some sense, the qualitative picture starts to look good. The last thing, as we, our ambition is really just to quantify, right? So how long does it take? How long are we going to take to actually, find like optimize this objective, right? And with the spirit of just trying to keep track of all the constants. All right. So for this, we now need to actually do a little bit of harmonic analysis. Okay, so remember what I told you for the single index model, that everything was driven by this information exponent, which was the first term in an expansion, right? And for those of you here who might be familiar with wavelets, this is really just similar to this number of vanishing moments, right? I'm just keeping track of how many, in a sense, how many terms are killed in this expansion, right? The first one. So how can we find the extension to several variables of this quantity? So the first thing that we do is that we replace, these Hermite polynomials. We can put all the Hermite polynomials of several variables. We can stack them all together into a tensor. Okay, so we can build this Hermite tensor the same way that we build the Hermite polynomials in terms of the derivatives of the Gaussian measure, right? So because this defines a tensor for the K, right, in Q variables that contains at every entry different Hermite polynomials of the same degree. But now formally we can do the same thing, right? Now we can look at the inner product. Now we can look at this expectation, right? And we can look at what is the first index, such that this inner product. So now this is going to define a tensor, right? It's going to be non-zero. But now when we have this tensor that is non-zero, we need to do something else that we didn't have to do before. Is that a tensor can be non-zero, but all the non-zeros can be concentrated in a smaller subspace. So in fact, instead of having Q variables that are visible through this tensor, I might have less than Q variables. So for this, we need to now define the span of this tensor, right? So I just view it as some kind of the range along each direction. This is, let me just say that this is a symmetric tensor, right? So we can define the span like without problem. So this defines a subspace that corresponds to what are the variables that are visible through this tensor. And now that we have this subspace, we need to introduce one last idea, which is the idea of filtration. Okay, and this is really what is going to be the key difference between the single index model and the multi-index model. And so given a subspace, right, so I give you already a subspace that I have to view that is inside the subspace that I'm trying to learn. Okay, so now I can define the same thing. I can define these inner products between Hermite tensors. But now I'm going to condition, right? I'm going to already pretend that I know everything that is in the subspace that I have already detected. Okay, so I'm going to define this expectation in a way that is conditional on the coefficient that I already know. So now these tensors now are only depend on the variable z that are outside, right? That are in the orthogonal of the subspace that I'm already finding, right? So in this picture, think that maybe I have already found some W1, and then I'm basically trying to look for directions that are outside of W1. Okay, so now we can define with this conditional tensor, we can again define what is the next information exponent. So what is the first j such that this quantity in fact is non-zero, and again we can define the span, right? We can define what is the set of new directions that are revealed after I do this filtration. Okay, so I can keep iterating this process, and in fact it's easy to see that this process has to terminate in a finite number of steps, and this defines a collection of numbers, right? So these are just a collection of degrees, right, that are revealed by these by these tensors, alongside the dimension of the subspace, that is the dimension of the subspace that is revealed at every iteration. And this is what we call what we call the leap exponents and dimensions, right? And the notion of the number of leap is because we are building from work that I'm going to refer to in the next slide. So now we have all the ingredients that are ready to explain the final result, right? So we consider, again, we have this family of dimensions and exponents. We consider an initialization of the subspace, right? So at the beginning, we are going to have a correlation with the ground truth that is going to be very bad, right? So it's going to be very, very close to the initial saddle point, right? So of the order of 1 over square root of d. And so the point here is that now gradient flow, we can, thanks to the previous decomposition, we have identified a collection of subspaces, right? That are these saddle points. And gradient flow is really going to do this kind of saddle to saddle trip, right? It's going to do it's going to travel from saddle to saddle. And the time it takes to escape each saddle is precisely given by the order of the saddle, okay? What that we define as this information exponent k. There's some interesting properties of these dynamics. First one is this cascade phenomenon, right? Is that if we have information exponents like leap exponents that are smaller or equal than a leap exponent that we have already seen, what it means is that then we have this kind of instantaneous learning, right? It's like the time it takes. So once I learn a very difficult structure, right? Once I have this thing there, I can immediately learn all the structures that depended on this previous structure, right? I can do that very fast if the associated leap exponent was smaller, okay? And in particular, this means that the total time where I can learn everything, right? The total time that it takes to correlate with the full subspace, in fact, is of the order of the largest leap, right? The largest leap exponent that we have defined. And interestingly, this leap exponent, this largest leap, it was already introduced in this paper by Emmanuel Abbé and Enrique Bosch and Theodore Bisekevich in the context of a simple, a very restricted class of target functions, right? And somehow what we are seeing here is that this is really driving the general dynamics for general multi-index functions. Okay, and let me also say that this statement, right, concerns how long does it take for gradient flow to escape in the population setting, right? So here we are still following this template that I described before, where we try to analyze very precisely the limit when you have infinite data. So then at some point you need to go back, right? You need to understand what is the impact of this formula of this result when you have finite amount of data. So using heuristics like that are kind of standard, like in high dimensional probability, one can do this translation and again go back to this, get this result that one should expect that when the number of samples is of the order of d to the L, right? Then the empirical gradient is tracking the population gradient enough to escape mediocrity. All right. So any questions at this point? Now I'm going to switch gears a little bit. So far I described what happens when one tries to learn these multi-index models with a gradient flow, right? With this two-layer architecture that we have adapted to the problem. Okay. So now that we have understood, we have explained how this algorithm performs in this problem, we can try to see how good is this algorithm, right? I mean, is there any method that could be better or that could be more appropriate for the particular problem that we are studying? So as I said, this gradient descent or a gradient flow or like the stochastic version, right, requires as a set of the order of d to the L samples to learn a multi-index model with leap exponent L. Okay. So is the sample complexity optimum? Even of course using polynomial time algorithms. So the answer is no, and it's not even optimum, even if one restricts our attention to algorithms that are what we call correlation statistical queries. So basically, these are algorithms that can interact with the data by asking questions that involve just looking at the label, looking at some transformation of the input, and just looking at the correlation, like the product of the label and the correlation. In fact, it's one can reduce this sample complexity from d to the L to d to the L over 2 by being smart, right? So using some form of like a smooth version of gradient descent. This is nice work by Damian. And as I will explain later, the reason for this economy can be also understood by using tools and ideas from tensor methods. We are going to see this in a few minutes. But more important, even more striking than that, there are certain examples that we have seen in the literature where one can in fact show that these kind of models, like both single index or multi-index, in fact can be learned with sample complexity that is linear in the data, right? So there's absolutely no dependency on this L at all. So it seems that this rate that gradient descent is exhibiting, in some cases, it can be avoided. So one thing that is interesting here is to understand, okay, what is the general lower bound? What is the true lower bound for generic link function, right? So can we get kind of a good description of what is the rate that you need to learn these functions? Okay, so for this we are going to now take a bit of a more general view of what is a multi-index model, right? It's the same thing as before, but with a little bit more level of generality. Okay, so we view now. We start with a distribution, right? That is in low dimensions, right? So it's a distribution on q plus 1 variables. And we ask this distribution to have a Gaussian marginal along the first q variables, right? So if you look at the marginal along the first q variables, it has to be Gaussian. And then just the other marginal, just assume that is a square integrable. So then we can define a Gaussian multi-index model as a joint distribution in d plus 1, right? So now d is really this high dimensional problem that has this planted structure, right? So I can view this joint distribution as basically having some component here that is not informative, right? So it's just some Gaussian features, right? Along certain, orthogonal to a certain subspace with a product with the informative part, right? Which is this joint distribution that relates this label with these low dimensional features. Okay, so in some sense, it's exactly what we had before. I mean, if you think that this joint distribution is just some, it's like so if you think that this is just if you just look at the distribution of y condition on z to be just a Dirac, then you recover exactly the same model that we had before. Okay, but obviously here you can have noise in the labels and you can have many different things. So in this language, the information exponent that we defined is just the smallest j, such that is again this tensor, right, is non-zero, right? So if x is actually a q-dimensional variable. So the goal in this problem, as before, is just I give you, we observe any IID samples from this distribution, right? With a planted, with a hidden subspace, and you want to recover this hidden subspace. Okay. And we want to understand is what is the inherent hardness of this problem, right? How expensive, how many samples do I need to observe to solve this problem efficiently? So for this, we are going to use this framework to understand the computational hardness of these kind of statistical problems based on the low degree method. Okay, so this is actually a very nice framework that has been developed by a number of researchers. So Sam Hopkins, Alex Wine, or maybe Afonso Bandeira and Tim Konitsky are some of the people that were leading some of the initial efforts, right? But it's a framework that is now quite popular. And so it's really designed to try to give a proper notion of how hard it is to solve a statistical inference problem task that goes beyond the standard worst case result that you have from, let's say, NP hardness. Okay, so the question is really now can be formulated in terms of detection, right? So rather than asking how expensive is to find the true W star, maybe we can ask for a simpler question, right? Is there any planted structure in the data or not? So this can be cast as a hypothesis testing, right? Between the hypothesis that there is planted structure, right? Maybe I have some prior over these directions, and then I just use this planted distribution, versus the null hypothesis that would say, in fact, the labels and the data are independent, right? So basically, there's no dependency between the label, between the Y's and the X. So the way this framework goes is that, in fact, one can extract read a lot of information about the hardness by looking at this particular projection of the likelihood ratio, right? So the likelihood ratio between signal and the null distribution, if I take this function and I project it into the space of polynomials of low degree, okay, and the degree of the polynomial corresponds to basically how many variables can I look at the time, right? So because I want to only study algorithms that are efficient, this degree is actually small, right, of the order of logarithmic in the number of points. So the way this conjecture is formulated by Sam Hopkins is that, in fact, if I look at this projection, this low degree projection of the likelihood ratio, if it's actually close to 1, right, intuitively you can see, right, if it's close to 1, it means that the two hypotheses are very hard to distinguish, right? So in fact, if this likelihood ratio projected in low degree is around 1, then there's no polynomial time algorithm that can distinguish these two distributions. Okay. All right. So to apply this thing to our setting, we need to understand how to compute this likelihood ratio. All right. And so in fact, this problem is not hard in our setting. Okay. So if we look at if we first fix one direction, right? So fix one of these planted directions, and we look at the likelihood ratio. In fact, you can use an expansion that again uses this like harmonic structure based on Hermite polynomials that we just described. Okay, so in fact, it's not hard to see that the likelihood ratio can be decomposed into into an expansion that separates the role of Y and X, right? And the role of X is just as before, it's just a Hermite polynomial. And then the dependency on the label on Y is through these conditional expectations. Okay, so now we have to actually compute the conditional expectation of a Hermite polynomial given Y, right? So now this becomes a function of the label, all right? So this is just a spare you the computation. This is just one line to show that this, where does this thing come from? But now that we have this expansion, right, and we try to relate it to the first expansion we saw at the beginning of the talk, it's very tempting to define a different exponent, okay? Which again, it will be the leading order of this expansion. Okay, and this is what we call this generative exponent. Okay, so the generative exponent is going to be the first k such that this coefficient, right, now you view it as a function, is going to be bigger, is going to be different from 0, right? So in particular, the L2 norm with respect to the marginal of Y has to be positive. All right, and so how does this exponent relate to the information exponent? Okay, so we have defined a different exponent. In what sense they are different from before? So remember, so this is the definition, and we can use this conditional expectation to rewrite the unconditional expectation that we had before, right? The information exponent. So the information exponent in this language just now becomes the inner product of this function zeta k with the linear function. Okay, so just to rephrase what I'm saying, the information exponent is just looking at the smallest k such that I have a non-zero correlation with linear functions, whereas the generative exponent just looks at the mere property that this function is non-zero. So obviously you can see that this k star is always going to be smaller or equal than L star, right? So in a sense, my exponent here is going to be, lower in general and potentially much, much lower. And in fact, we can obtain a variational representation, right? So there's even a more explicit connection between these two. So I can view this generative exponent as the smallest information exponent that I can obtain by taking my label and applying any transformation on my label. Okay, so I can look at my data x and y. So I told you before that I can compute the information exponent by just looking at correlation of y with Hermite polynomials. But now I'm saying that you can do something that is maybe a better idea, that is to consider any possible label transformation, right, this t, and then look at the smallest information exponent that one gets out of these possible transformations. Okay, so this is the generative exponent. Let me say that in the case where this exponent is 2, right, the particular setting where one plugs here Hermite polynomials of degree 2, this is an object that was studied in this very nice paper by Marco Mondelli and Andrea Montanari, and also some works by Lenka and Flohan group. And so some examples, right, just to maybe to help you get the gist, right, in what sense they are different, is that if I have a polynomial, then the generative exponent is always going to be at most 2, right? So if the polynomial is even, I have the generative exponent 2, and if the polynomial is not even, then it's 1, okay? Obviously, this is a big contrast with the information exponent, right? Because we saw that the information exponent of a Hermite polynomial is going to be the degree of the polynomial, right? Whereas here we see that it's either 1 or 2. We can also build explicit functions that have a generative exponent bigger than 2. This is like this presume like weirdly looking function. It turns out that this has a generative exponent 4. And in fact, one can actually build functions that have an arbitrary generative exponent. But the bottom line here, and I want to convey this, is that one needs to work very hard to construct an example where the generative exponent is bigger than 2. Okay, and this is something good to keep in mind. All right, there's also an extension of this generative exponent to multi-index functions, right? So first here we have described the setting where you have a single scalar function. We can do the same thing. In the interest of time, maybe I'm going to just very briefly describe it here. It's basically the same thing, right? So we start with the likelihood ratio. We can express this likelihood ratio in terms of an expansion that now involves these Hermite tensors, right? And now this function that we define, right, this zeta k of y, it's a more complicated function because now it's tensor valued, right? So for every y, I have a tensor for the k. Okay, but nonetheless, I can still look at the order of the tensor such that this function is non-zero. And again, similarly as before, I can use this tensor to define a subspace associated with this tensor, which is its span. Okay, and I can use again the same idea of the filtration, right? So once I have the subspace, I can redefine what I mean by what I mean by input and what I mean by outputs, right? And then basically, once I have a subspace, it becomes a label, right? It becomes something that I can observe, right? So I just define my label to contain the y and then everything that I have already observed, right? So once I do this thing, I can just formally repeat the same decomposition and iterate, right? So same as before, I get kind of this sequence, that finite sequence of exponents alongside with subspaces. So we can again define the exponent, the leap exponent, as just the largest leap exponent over the sequence. All right, so now what can we do with this object? So in fact, we can show that this leap generative exponent is the one that drives the complexity. So there's a lower bound, again, using this low degree framework, right? So that says that according to the low degree framework, if I have a number of samples that is smaller than this d to the k star over 2, then there's evidence that there's no polynomial time algorithm that is able to detect this planted multi-index structure. Okay. And just a little thing, right? For the multi-index setting, we need to do a little bit. We need to do a little trick, right? So in the multi-index setting, the hypothesis testing is between two planted models, one that has the right number of dimensions and one that has a smaller number of dimensions, right? And with the null hypothesis is kind of optimized, is basically placed so that the detection has to overcome the largest slip, right? So that's why you have here the largest slip. For those of you who might be familiar, this lower bound in the low degree method is in fact matching exactly the lower bound that comes from the similar problem, that is the tensor PCA. And also the same kind of technology, one can use it to define SQ lower bounds. Okay, so SQ lower bounds is for those of you who are not familiar, it's basically a similar it's a similar computational class. It's in some sense, it's similar than the low degree method, but using a slightly different notion for computation oracles. And also as an immediate conclusion, because if I consider estimators that are brute force, right? So because the number of parameters that I'm planting in the model obviously is linear in dimension, it's a subspace, right? It's a subspace of fixed dimension Q, right? So the number of parameters is proportional to D. So just brute forcing leads to obviously a sample complexity that is linear in D, but obviously as soon as K star is bigger than 2, there's a computational gap, right? There's a statistical to computational gap. All right, and we're almost done. In the last 5 minutes, let me just describe whether this lower bound is tight or not. So, so the first thing we consider, right? Let me first focus on the single index setting. So the first thing that we do is that, as I said, right, the first thing that we do is to consider a label transformation that somehow maps the generative exponent to the information exponent, right? So we can just consider this label transformation using this optimal transformation as zeta k star, so that now we have a non-zero correlation, right, between the transform labels and the Hermite features. So once we have that, we can consider this tensor, right? So we can build this tensor that just is averaging these transform labels with Hermite features on the input. And so because I have this non-zero correlation here, what it means is that in expectation, this tensor has a spike, right? So there's a direction. So the direction in which the data lives, in fact, is visible through this expectation. Okay. So in that sense, I can view this T1 as a noisy, kind of as a spiked noisy tensor, right? So in that sense, it's very similar in spirit to the tensor PCA problem, right? Where I have some kind of noisy tensor with a spike. Looks a little bit like this in the surface, right? And so how can we efficiently recover a spike from a tensor? So here again, building from the literature in tensor PCA, it's natural to use what's called the partial trace, okay, which is a way to map this tensor to a matrix and then use a spectral method in this matrix. Okay, so the partial trace is just basically going to average over all the entries of the tensor except for 2, right? So that you can define a matrix, and then this defines an estimator that is just the largest eigenvector of this matrix of the partial trace. And so the conclusion here is that if you apply this method, right, you can recover the planted direction with sample complexity that is basically matching the low degree lower bound, right? It's the d to the k star over 2. And so in terms of analysis, right, as I said, it's reminiscent of tensor PCA. So at the surface, it's actually quite similar, but there's a difference, right? Is that in tensor PCA, the entries of the tensor are IID Gaussian noise. Here, the entries of the tensor are these like potentially high degree polynomials, right? And they introduce a lot of correlation in the input, right? So the entries are heavy-tailed and correlated. But nonetheless, we can use tools from Gaussian universality, right? These recent results from Ramon van Hendel to actually establish this the fact that this algorithm is going to succeed at that rate. All right, I don't have a lot of time, so maybe I'm just going to very briefly say that one can do the same thing for the multi-index setting, right? By having a kind of a smart extension of the partial trace, right? So the partial trace on a slightly different matrix basically gives you the same idea. So just to start recapping, right? Just the final summary of the results. So basically what I presented is that essentially 4 set of results, right? So this is a kind of this is like the work of Gérard Benarrouz and David Daniel Su, etc. So if one focuses on gradient flow, if one wants to go from the guarantees in single index to guarantees in multiple index, what is important is to understand this notion of filtration, right? And so in this setting, we have a single saddle point. And then when we go to the multi-index, we have this kind of different dynamics, which is the saddle to saddle dynamics, right? And so that's one step. And then if one wants to improve the performance, like the sample complexity of these algorithms, there are basically 2 things that one needs to do. The first one is to apply this label transformation that is going to, remove the influence of this information exponent and reveal the true exponent, which is this generative exponent. And then this idea of partial trace for the experts. Is actually the thing that gives you kind of the optimal noise averaging, right? So that you can actually gain this extra factor of 2 in the rate. Okay, that you would, if you were just doing tensor power iteration, you would still have this dependency that doesn't have a factor. So just as a summary, right? So I guess what I told you is that it's kind of this picture that I described, and there's certain things that I think could be interesting as follow-ups. So first is that we have to use this kind of algorithm that first optimizes the second layer weights perfectly and then plugs them back into the first layer. So whether this is necessary or not is an open question. Would be interesting to understand it better. And then there's also something interesting is that I told you that that this label transformation is completely crucial to remove this dependency on the information exponent. There's also some very nice recent works from Yatin Dandi and others, and then Denny Wu and Jason also has a recent paper where they show that in fact, if you just do a gradient descent, but we are using batches several times, one can implement something that looks similar to this label transformation, right? And also remove the influence of the information exponent. And then the last thing, kind of the elephant in the room here, is that everything here is building heavily on the Gaussian data, right? So there's all these, tools that I use are heavily based on, doing harmonic analysis over Hermite space, right? So how can we actually extend these things to general distributions? That's also an interesting question for future work. So with that, thank you very much. And yeah, maybe apologies that I went a couple of minutes late. So